Hi ladies and gentlemen, in this video we are going to look at the rest of section 2.1 where we are going to talk about Venn diagrams and set operations. Again, here is your homework for this part. Also, you can look at examples 2.8, 2.9 and 2.10, and also you can look at explanatory exercises. But as I told you before, this question will not be discussed in class. But if you send me or the Twitters your work showing that you tried the exercise, we will help you with the answers. In this part, we are going to talk about set operations, union of two events, intersection of two events, complement of an event, define mutually exclusive events, and we will construct a Venn diagram to depict events. We will use Venn diagram to verify De Morgan's laws, and we will extend the operations of union and intersection to more than two event. Let's look at what you have learned so far. You know the definitions of experiment, sample space and event. Experiment is any action or process that its outcome is not known in advance, but we know about all the possible outcomes of the experiments as a sample space of experiment, and you know about the event, any subset of sample space. If it has one element, it's called a simple event, or if it has more than one element, it calls compound event. But what's the meaning of happening of an event? If we conduct an experiment and the observed outcome belongs to an event, then we say that event has happened. But look at this example. Suppose that the experiment is throwing two coins. So as we discussed before, the sample space is HH, HT, TH, and TT. Suppose we have two events, a simple event consisting of HH and a compound event consisting of HH, HT, and TH. So if the observed result is, for example, HT, it means heads for the first coin and tails for the second coin, then you can see HT here, but not in A. So we can say B has happened, A has not happened. But if the observed result is HH, you can see HH in both A and B. So we can say A and B have happened. Okay, let's continue. What is a Venn diagram? Is pictorial representation of events. For example, suppose an experiment of rolling a dice. So the sample space is 1, 2, 3, 4, 5, and 6. Let A be the event that an even number is observed. So A is 2, 4, 6, the even outcomes. And let B a multiple of 3. If a multiple of 3 is observed, so B is 3 and 6. So how we plot a Venn diagram? Again, we had a sample space 1, 2, 3, 4, 5, 6. A is even numbers and B is multiples of 3. Okay, now we need a rectangle to represent the sample space. So we have 1, 2, 3, 4, 5, 6. And for representing events, we need some circles. For example, for A, it's A, and for B, it's B. Now we have a Venn diagram for these events. As you can see, 1 and 5 don't belong to A or B. Interpretation of regions in Venn diagram is so important. So look at this example. A manufacturer of small motors is concerned with 3 major types of defects. A is the event that the shaft size is too large. B is the event that the windings are improper, and C is the event that the electrical connections are unsatisfactory. Please note that when A, B, and C show the defects, so it means in white region here there is no defect and the products here are perfect. Now we are going to interpret the following regions in this Venn diagram: the pink region, yellow and orange region together, orange, blue, green and white. It means 3, 5, 6 and 8. For the first one, look at the pink region. This region is contained in A and B but not in C, so it represents the event that the shaft is too large and the windings are improper, but the electrical connections are satisfactory. Now look at region 1 and 3 together, this area. This region is common to B and C and partially A. It represents the event that the windings are improper, the electrical connections are unsatisfactory, and also there are some shaft sizes that are too large. And now look at the regions 8, 6, 3 and 5. This area. Since this entire region falls outside A, it represents the event that shaft size is not too large in this area. Now we are going to explain set operations. We start with complement of event A. It is shown by A prime or A bar, but A prime, we are going to use A prime. Complement of A is all outcomes in the sample space that are not in event A. Look at this example. Again, we have a sample space related to rolling a dice. A is or represent the even numbers in S, 2, 4, 6. So A prime is odd numbers in S. It means 1, 3, and 5. So again, all outcomes in sample space that are not in event A. Intersection of events. Intersection of events A and B is all outcomes in the sample space that are in A and B, this region. All outcomes in the sample space that are in A and B. Union of events A and B is all outcome in the sample space that are in A or B or both. All this area. All the outcomes in the sample space that are in A, B or both. Please note that if one element of A union B observed, it means at least one of A or B has happened. Now look at this example. We are going to obtain intersection of A and B and union of A and B for this example. We have it here. So for example, intersection of A and B, it's this area. So it's 6, and for union of A and B, it's this area. All the outcomes that are in A and B or both of them. So 2, 3, 4, and 6. Or also we want to, for example, obtain B prime. It means all the outcomes in sample space that are not in B. So it's this area. They are not in B. So the result is 1, 2, 4, and 5. Okay. You can see the results here. But what is mutually exclusive or disjoint events? Events A and B are mutually exclusive or disjoint if A and B have no outcomes in common. It means the intersection of A and B is empty or null. You can see that they don't have any outcomes in common. So for example, here if we we have another events like for example 1 and 2, then B, intersection of B and C is empty, so B and C are mutually disjoint. Look at here, A and B. In this example, the intersection of A and B is not empty or a null, so A and B are not disjoint.